So we are going to start with a simple application of the code, of the VPSC code, to simulate tension and compression of an FCC polycrystal. And hopefully you will see how some of the features of the code affect the outcome. To start with, I think that you have already been able to compile the code. I hope. Have you done that? If not, you have to run this command. You have to run this command to compile it with G-Fortran. Does everybody have the who doesn't have the compiled code? So we can wait, or okay. So you have the compiled code. You have it in a directory called VPSC8, let's say, because the examples, we are going to go and pick files from the examples that are subfolders of that directory. Anyway, before we start, I want to explain things. The input files for the code are always, and there may be others, but they are always what is the initial texture, which is a discrete orientation file with a certain number of grains, typically 1,000 grains, let's say. When we started doing this type of calculations, we couldn't afford to do more than 100 grains because the computers were really slow and took a long time. But now the computers can deal with thousands of grains without really much of an issue, no? Not only that, we would work with 100 grains, leave the code running, and come back the next day to see what the result was, because it takes hours and hours to give a result. Now it's seconds. So you will have a texture file, typically. You will have a file that tells the code what are the slip systems and the symmetry of the crystal that you want to solve, and what are the hardening parameters, that is the constitutive law. So on one side there is the crystallography, and after that there is going to be the constitutive law in that file. And then the macroscopic boundary condition, which is which problem do you want to solve. The nice thing about this is one nice thing about the interaction equation. I'm going to go back a few slides. The nice thing about this equation is that you don't need to enforce the whole strain rate tensor or the whole macroscopic stress tensor. You can enforce some components of stress and some components of strain rate, and that is a very with a Taylor model. With a Taylor model, you cannot do that. That is, you can do that, but you have to do that because you have to impose strain rates in the Taylor model. You have to impose a strain rate and then figure out what is the stresses that you get and if they are according to the boundary condition. So in a tensile test, you know that you impose this stress, the tensile stress, but that the lateral stresses are 0. But there is no way to tell in a Taylor calculation to impose 0 stresses. So you will have to impose a strain rate that eventually gives you 0 stresses, 0 lateral stresses. But you can only do that iteratively. Here, that is built in the interaction equation. The conditions, the boundary conditions, are here, and so when you solve, everything, all your knowns are on one side, and all your unknowns are going to go to the other side of the equation. So as part of the macroscopic boundary conditions, you can introduce a strain history. We are going to see in one of the examples for rolling how you introduce a strain history, but probably not today. Now, one thing that you should know is all the input used in the simulations is copied in a file called runlog.out. This is very useful because when you run your code, what I usually do is I rename the runlog.out runlog case 1, runlog case 2, runlog case 3, and all the conditions that I use to run a particular for a particular run are in that file. So together with the other output files. So all the other output files are renamed case 1, case 2, case 3. But I know what are the conditions that I use. So this is a very useful file. It is also used to write some extra information. I mean, and you can use it yourself to write some extra information. If you use the command write 10 whatever, so 10 is the unit run log. Dot out. So when you are testing your code, you want to see what is happening in a particular grain. You can run stuff about that grain in that unit run log and check it there. So it's another option that you have. Then you have of course, texture file. You have the final texture after the run. You can also get intermediate textures. There is a way of printing intermediate textures during your run every so often. You get stress strain evolution. You get what is the activity in the different slip and twinning systems. This is useful especially in non-cubic materials where you have different deformation modes and you want to know how much each one contributes. I don't know, in magnesium, how much the basal contributes as opposed to the pyramidal system or the prismatic system or the twin system, how much each of them is contributing to the particular deformation that you impose. And you can calculate yield surfaces or yield losses, and you can calculate Langford coefficients. We are going to go over these capabilities in the examples. So the driver file for the code is bpsca.in. This file declares what are the files that need to be read, that are going to be read, and what are the conditions of the run, what are the parameters of the run. So I'll explain. What is in red? What is in red is what you will be using during these examples. The others, I can go into that, but you're not going to be using the other parameters during the examples. So this is a leftover from other time, the number of elements. I mean, we only have one element. This was meant for running the code with a finite element code, but it was just left there. Now, number of phases. You can run an aggregate that has several phases. It doesn't have to be only one phase. It can be a combination of FCC and BCC, or FCC and HCP. You can run several phases, and so you declare the number of phases that you're going to run and the volume fraction of those phases. In this case, we're going to run only one phase and the volume fraction is 1. Then there is information about the grain shape. That is the information about the ellipsoid. You are going to be, what is the initial shape of the ellipsoid that represents the grain. We usually start with a spherical shape, but you don't have to start with a spherical shape. And this shape can have an orientation, so it can be oriented at an angle with respect to the testing axis. So you give the Euler angles of the ellipsoid, and you also tell what is the eccentricity of the ellipsoid. So what is the length of the axis A, B, and C. So that is what goes into that information. And as I said, for a moment we are not going to play with that, but if you are very welcome to play with those things, and we can discuss results. For example, one interesting result is the dragging effect. The dragging effect is such that if you, let's say, you have a material here with a grain that is elliptical, and you are doing compression. This grain is going to tend to adopt this shape. The shape is going to reorient in this direction because you are doing compression. So the material around it will tend to rotate this grain around. And that is that term that appeared there, the W tilde. You remember we had a W plus a W tilde. This W tilde is the one that is contributing to this effect. So you can drag a grain just because of the shape. And of course, if you rotate the shape of the grain, the crystal inside the grain is going to rotate. So the orientation is going to change rapidly in this grain. So this effect is captured by the inclusion formalism, for example. So, as I said, this is information about the grain shape and orientation. Now, this is important, the name and path of the texture file in the example that we are going to run. The file is in the example 2 for FCC, and it's called rand500.txt, which is a random file of 500 grains. Then there is the name of the single crystal file, which in our case is a generic FCC, full face center cubic single crystal, which has also the hardening parameters. Now, these two parameters I recover and I save you are not going to be using them, but they are meant for running the code, stopping at some point, writing down the state of the material, and then being able to run that, to use that as the initial state for running another process. Originally, it was put there because as the code was taking so long to process, sometimes you wanted to do tension in one direction and then do compression in another direction, for example, and then you wanted to save the tension status of the code and then do compression on that one. Now the code runs so fast that those things are not necessary, but other things can be done with this, but I'm not going to get into that. This is to calculate rolling components. This only applies to rolling of FCC materials. We are going to show an example, but you can also calculate what is the volume fraction of rolling components during the running simulation. This is the frequency of texture downloads. As I said, the code will always write texture at the end of a process. That is what the 0 stands for. The zero is my default. But you can write texture every 20 incremental steps or 30 incremental steps, and the code will tell you how the texture is evolving. You can plot that. This is the interaction I mentioned before. So you can use the full constraints or Taylor model. You can use the affine, which is a way of something like a tangent model. The secant, the ineffective, the tangent. We can play with that. We can play with that, or you can play with that. We are going to use in the example the tangent and the secant for a moment. You can update orientation, grain shape, and hardening. That is, one in this case is that you are going to update orientation, grain shape, and hardening. But I'm going to propose you that you play with this parameter. What happens if I don't reorient my grains? I only harden my grains and don't reorient them, or the other way around. If I don't harden my grains but I reorient them, how does the thing change? What happens if I don't change the shape of my grain? I leave it spherical throughout the deformation, things like that. You can play with those parameters. Then there is a number of processes that you are going to be performing in the simulation, and what follows is all the processes that you are going to perform. In this case, we are just going to do tension and compression, so there is only one process, but I'm going to show in other examples that how you do several processes in a sequence. For example, you can do tension up to 50%, and at that point say, okay, calculate the polycrystal yield surface, and then do 50% more of tension, calculate again the polycrystal yield surface. So that would be 4 processes: 50% calculate polycrystal yield surface, 50% calculate. So you do 100% tension with 2 calculations of polycrystal yield surface. So those are called processes, and those processes can include a rigid rotation. You say, okay, do compression 30%, rotate the material rigidly 90 degrees, and do another compression test. Rotate again 90 degrees, do another compression test. So that is also called considered a process. So you can do a sequence of these processes in the simulation. As far as, of course, you are looking at the same material and you are playing with the same material. You cannot change your material on the fly. So, and these files you are going to, the input files you are going to find in the subfolder example 2 FCC. So this example, let me see. Let me describe this file first. This is the texture file. The texture file has a simple structure. I mean, it has essentially 3 lines that are left there just to put information that may be relevant to what this texture is, where it came from, whatever. And then it has a letter that is read here that indicates what is the convention used to represent the Euler angles. The code allows for 3 different conventions to represent the Euler angles. It can read files written in 3 different conventions. And the conventions depend on how you define your rotations, the rotations of your crystal, in order to put it in the final position. So you remember that we were showing we were showing that, in particular, the Euler convention is you have a first rotation by an angle phi1, which would be this angle around the axis 3, then around this then around this axis of the crystal, you have a rotation of capital phi, which is this other angle, and then around this axis, you have a rotation of phi2, which is this angle. And here you give what is the relative weight of that grain. In this case, it's a random texture. All the grains have the same weight, 1. Inside the code, this gets normalized to 1, all the volume fraction, but it doesn't have to be add up to 1 to start with. So this is phi1, phi2, and the weight of the grain. So this is the random texture that we are going to be using. These are the poles 100, 110, 111. As an exercise later, I say, well, why don't you try to reproduce this using pole 8 as a way of practicing with pole 8. So we go back. We go back to the problem that we want to solve here, which is simulate extrusion, tension, and compression. I mean, compression is not extrusion. It would be more axisymmetric. So simulate deformation where the lateral strains are the same. So in extrusion, you put your sample through a circular die, and of course it forces both lateral strain components to be the same. So that is the process. In compression, let's assume that you can do something similar. So we enforce that condition. We don't have to, but we enforce that condition. We are going to consider slip in the 110 and 111 planes, which we have 12 systems with that characteristic in cubics. For the Voce hardening, we are going to be using a non-hardening hardening. So only tau 0 is equal to 1, and then all the other parameters are 0, which means that the tau doesn't change during the process. The tau critical is flat and has a value 1. Now, a value 1, the units in the code are arbitrary. So 1 can be whichever unit you want, but everything that is stress will be treated in the same unit, considered to be in the same unit. Everything that is strain rate will be, typically we think in 1/2, but you can use 1/hour if you want, but because the code in itself doesn't have units. But you have to be consistent when you enter your parameters, that all the parameters are in the same units. So if I were to put something that has to do with elastic constants, and I provide the information of elastic constants in GPa, then a 1 here will be 1 GPa, for example. So we are going to impose a velocity gradient like this. So one in the direction 3 and minus 0.5 minus 0.5. It has to be incompressible. So the diagonal has to be 0 plasticity. And as I say here, what I will ask you to do, if you want to practice with the code, eventually reproduce the simulations that are in that example too. Reproduce all those simulations. You will have the results, and you also have you will have here the plots of the output, but also in that older version of the manual, you will find the results and the plots. Just for you to play with the code. We are going to do a couple of these cases today here. and then compare the textures that you obtain, the sleep system activity, see what happens if you change the hardening law. If you change the hardening law, you will see that it doesn't change the texture that you get or the system activity. It only changes the stress strain curve, but because we are enforcing the same gammas, the same gamma dots in each system, it doesn't matter how hard it is. Geometrically, in order to accommodate that deformation, you will have to enforce the same gamma dots no matter what the hardening law is. So the system activity and the texture will not change, but you can verify that that's the case. And then you can play a bit with suppressing the grain reorientation and the shape orientation and compare results. What happens if I do that or not? Okay. So I talked about this one already. Okay, so this is the description of the process file. This is the file called tension extrusion 3 that you are going to run. It has 50 steps of 2% axial strain along the direction 3. Now, how do you enter that information? Okay. The process file looks something like this. So the first number is the number of steps that you are going to run. The second number is the control direction. So that is the strain that you are going to control is the component 3, and here we use the void convention, where you have 1, 1, 2, 2, 3, 3, 1, 3, sorry, 2, 3, 1, 3, 1, 2. So the void convention says this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. So putting there, saying that you control the component 3 means that you control epsilon dot 3, 3. Or maybe sigma 3, 3. We will see how that is controlled, but we are not going to do creep. If you control the stress, then it is creep. It is a creep simulation. We are not going to be doing those examples, but you can do those with the code. You can also control stress, and then you can do a creep simulation. So then the control increment is the increment of the component that you are enforcing, which in this case is the component 3. So it's 2%. The control increment, epsilon 3, 3, is the component that you are enforcing, is 2%. And this is the initial and final temperature. For these examples, this doesn't really matter because we don't have anything that depends on the temperature here, but if your constitutive law depends on the temperature, and there are some in the examples that do depend on the temperature. If your constitutive law depends on the temperature, then you need to give what is the temperature at which you are running your test, and if your test runs with temperature evolving, you have to say what is initial and the final. Initial and final temperature. So this is an important parameter because these tell the code which are the components that are being enforced of the velocity gradient. So if you have your velocity gradient, Lij, so L11, L21, L31, 1, 2, L2, 2, L3, 2, L1, 3, L2, 3, L3, 3. What we said is this is the macroscopic one. We said that there is an epsilon dot average plus an omega average. The three you have to enforce three of the velocity grade. So you have nine components in these tensors, but you can only enforce 6, and the reason is if you want to enforce all 9 components, what this tensor does for you is, you remember that I showed before that a spherical element transforms into an elliptical element through the velocity gradient. But any rigid rotation of this element, like this or like this, is not relevant to the plasticity deformation. So there are always 3 components of the off diagonal that have to be enforced in this tensor, because not doing so means that you are trying to simulate something where you rigidly rotate your sample, and that is not a process that you can simulate. It's like you say, okay, I'm doing this test where I had my laboratory axis as a reference, I have my testing machine, and while I'm doing my test in the testing machine, I'm also rotating the testing machine. I mean, that doesn't make much sense for a simulation. Or if you want to do that, then finally you can say, okay, and I'm going to put that rotation, superimpose that rotation to whatever I get later. But you're referring your texture to the laboratory axis. But if you are cheating and rotating all your testing frame, your texture with respect to the laboratory axis will change, but just because you are just rotating your sample rigidly. So anyway, point is, of the off-diagonal components, three of them have to be enforced to be 1. How do we enforce the components? Well, this IU dot, unfortunately, this is an old notation that stayed in the code, but IU dot is really Lij. This is what U dot, because it's UI dot, is and IU dot being 1 or 0 is telling the code if you are enforcing this component or not. 1 is yes, you are enforcing this component, and 0 is no, I'm not enforcing this component. And then here you give the values of the components that you are enforcing here. This is a U dot. In this particular case, all of them are enforced, and they are 1, -5, -5, and all zeros here. Okay? So this is, and of course, the same with the Cauchy stress, sigma 11, sigma 22, sigma 33. If this tells which are the stress components that you are enforcing, which is known because this is 0, and this is the value of the components that you are enforcing. as a matter of fact, these are zeros because you don't know what they are. You are not enforcing them. They are going to be a consequence of the simulation. And then delta epsilon is going to be epsilon dot times delta t. So if you enforce this component, epsilon, this component, the component 3, and if you enforce that the increment of that component has to be 2%, from here you calculate the delta t. The delta t is a consequence of enforcing the velocity and the total increment. I think I have already discussed this, but now how do these hardening parameters enter into the single crystal file? Okay, this file is called FCCSX. So the single crystal files have a declaration here, which is only for reminders. It has a declaration that is read, that tells what is the symmetry of the crystal. The code can deal with any of the 7 primitive symmetries. It can be cubic, it can be hexagonal, can be trigonal, tetragonal, triclinic, or orthorhombic, and monoclinic. So the code can, and each of those have a number internally, but you declare that as cubic, trigonal, tetragonal, and the code will read it and recognize it as the symmetry that it has to use. It is important to convert the Miller indices into actual vectors and planes. So it is important to know what is the shape of the primitive cell or the single crystal primitive cell. No? In the case of the cubics, it's not much of an issue. The unit cell axis have values 1, 1, and 1, and the angle between them is 90, 90, and 90. So it's a cube. It is a cube. So if it could be, if it were an orthorhombic material, you would be giving these triangles A, B, and C, or so you give 3 different values. If it is a monoclinic, this angle will not be 90 degrees. This angle will be maybe 80 degrees. So you give this information in that line. Now you will read the elastic constants of the material, and these dots means that I have suppressed lines there, so this fits in the slide. But you read the elastic constants of the material. In principle, the elastic constants are required if you are going to calculate directional Young modulus in a roll, especially in a roll material, you may want to calculate directional Young modulus, or if you are running the code in the thermoelastic version. If you are running the thermoelastic capability of the code, then you need your elastic constants and your thermal expansion coefficients. Then you read the information about slip and twinning modes. Now, as you can see here, there are dots, so it means that there is a lot of lines that I have omitted there. What you put here is the total number of modes listed in the file. So you may have, in the cubics, you may have 2 or 3. In the hexagonals, you may have 6 or 7. In the orthorhombic, you may have 10, for example, total number of modes listed. And then you are going to say how many of these modes are going to be used in the calculation. You don't need to use all of them. You say how many you are going to use, that is this line. And then you have to put here a list of the ones that you are going to use. So I'm going to use mode 1, 3, and 7, for example. So I use 3 modes, 1, 3, and 7. The idea of that is that you use always the same file for that. You don't have to just keep putting things in and out of the file. You just use the same file, and you just pick, I'm going to use this, and this. And then after you have read all the sleep modes, then it comes the constitutive law. Okay, the constitutive law is recognized by an identifier, which is 0 for the Voce law, 1 for the MTS law, and there are several other laws in the code. I mean, they are not listed there, but you have several other laws, which in the examples that you have will be properly listed. So you say, I'm going to use the Voce law. This is important because each law, each constitutive law in the code, has a specific subroutine. So that subroutine is used to update the critical stresses in the systems. So you need to, when it comes to update the critical stresses in the systems, you have to send the code to the right subroutine. Here is if you want to use the rate sensitivity. I'm not going to get into that now. You just use one. One is yes, 0 is no. So yes, use the rate sensitivity. It has to do with the fact that you have a factor n here, and you have a m sigma over tau. So if epsilon dot is proportional to this, if you enforce epsilon dot 10 to the minus 3, you are going to get a value of sigma. Now, if you enforce it epsilon dot 10 to the 3, your sigma will have to increase in order to give you 6 orders of magnitude more strain rate. You go from 10 to the minus 3 to 10 to the 3. So your sigma will have to increase. And that is a rate sensitive effect. I mean, rate sensitivity is when in your hardening curves at 10 to the minus 3 look like this, and they may look like that at 10 to the 3. So in order to get this effect, which is mediated by this parameter n. Now, in general, you will leave that on, but if this tau, because your constitutive law is more complex, is a function of the strain rate, if this law is a function of the strain rate, you don't want to have two effects, one coming from here and the other coming from here. So if you use the rate sensitivity equals 0, it eliminates the effect that is coming from this value n, essentially. And it uses the rate sensitivity dependence or the rate dependence that you put in the parameter tau. Yes? The critical stress. Yes, and the critical stress in general, yes, it's going to be a function of how fast you want to deform your material. So it's a function of that. Sometimes you can mimic that with this parameter n, but only in limited ranges of rates. If you really want to do that for the extended range of rates, it is better to do that, to put that dependence here. And yeah, in the examples in the code, you will see the MTS model and also the dislocation density model. Those models have the ray sensitivity introduced in the taus, and so they eliminate the ray sensitivity coming from this cell. I mean, all these are things that I mentioned, so you know more or less what is the extent of features that the code has. For the examples that we are going to do, we are not going probably to go too complicated, but just for you to have an idea of the capabilities. And then grain size. I mean, grain size only matters if your law has a grain size dependence. If it doesn't have a grain size dependence, it doesn't matter what you put there. And then you look at, this is just a title for the 111-110 slip. What are the parameters that you are going to use? So you say that you are going to use a parameter n, which is this n for that system, which is 20 in that case. Then you give the values of tau 0, tau 1, theta 0, theta 1 in the Voce law. This is the whole page factor if you are going to consider whole page effects for grain size. And then the latent hardening coefficients, these are the HSS prime. Well, I had them there. These are the HSS prime that appear there. Okay. So I think that we have described all the laws. So what do we get when we run this code? Well, the first thing is in this example, the code was run for all the possible interactions that are available, intention and compression, to highlight what is the difference between using each condition. So what is plotted here is the stress strain evolution and for tension and compression, and the activity of slip systems. I come to explain. First, the stress strain evolution. If you these are the different interactions that you can use. Taylor is a very stiff interaction, meaning that because you force every grain to deform the same, it means that the grain doesn't have any freedom to deform more or less. In a way, it is the case where the surrounding matrix is forcing the inclusion to deform exactly as the matrix is telling. So that is Taylor, and secant is close to that because the stiffness of the medium is very high in secant. The M tangent, the M parameter is small. The compliance is small, so the stiffness is high in the case of the secant, and so the medium is going to deform to force the inclusion really to deform as the medium is deforming. So what happens is that gives higher stresses, both for the Taylor and the secant, gives higher and very close to each other, both in tension and compression. And the evolution and increase here has to do with the fact that the texture is evolving. So there is no hardening at the grain level. The Voce law is 1 all the time. So any change in the yield stress is coming from a stress effect, from a texture effect. So that is what is called texture hardening. That illustrates texture hardening. I mean, you can have hardening in the macroscopic flow curve just because you are evolving your texture. And more grains are oriented to orientations where they are harder to deform. That's texture hardening. So all the other laws have larger compliances and to different extents, and give stress strength curves that are noticeably lower than the upper bound of Taylor or the secant. Compression, there is a bit more dispersion. Now, this is slip activity, and this I need to explain a bit because the definition is simple, but I don't think I have it in the slides. So you have gamma dot in every system in the grains, and they say that S goes from 1 to 12, okay? So in each grain, then you look at gamma dot S maximum. Which one is the S star? Is the maximum? Which one is the maximum? And then any system that is lower than 0.05 gamma dot, any system gamma dot S that is lower than 5% of the gamma dot S maximum, you say that that system is not going to be counted as active. So that is how that is defined. This is just a line in one subroutine. If you want to change it, you can change it, but that is the criterion. Anything that contributes less than 5% of the shear of the maximum system is not counted as active. And then that gives you a number, the number of active systems in the grain. And then you make the average of the number of active systems in the grains. Over all the grains, you make an average of that number, and that is what is plotted in the system activity. It's a general measure of how many systems are active in average per grain, how many systems are being activated per grain. And as you can see, it is clear here also that the models that are close to the Taylor model that force the deformation to be the macroscopic one require more systems per grain, while the others don't. And the reason is, when you have to deform in axisymmetric tension or axisymmetric compression, the grain, it requires for the grain to activate about 5 or 6 systems, because well, this is cubic, is 6, the maximum. But if the grain is left free to choose how it wants to accommodate the deformation, sometimes the grain prefers to, instead of deforming in an axisymmetric way, so squeezing like this and stretching like that, the grain, or if you compress it, compressing and expanding the same in both directions, the grain prefers to deform by shearing in subsystems. So it may get, when you compress it, it may get an oval section instead of a circular section. It develops an oval section. And the rest of the deformation is accommodated by the surrounding medium. But that happens if the surrounding medium is compliant. If the surrounding medium is not compliant, it's very stiff, it forces the grain to deform axisymmetrically. So that is what is going on here. What is going on here is that the grains choose to deform not as the macroscopic strain, but choose more to deform in plane strain, and because you have many grains, in average, they give you an axisymmetric deformation, in average. But each grain is not deforming axisymmetrically. So that is another nice thing of this self-consistent model based on the inclusion formalism, that it really captures the relative stiffness between the grain and the surrounding medium, and searches to accommodate the deformation of the grain and the medium in order to minimize the stress that you need to deform the grain. So not much more to be said about this. The exercise for you to do will be to plot the stress component. We will go over these examples now to plot the stress component, so you will get something like this for the secant and the tangent case only, and plot the slip activity. They are in the files stress strain dot out and activity of phase 1 dot out. Okay. What about the textures? You will be getting also. You will be getting the textures of this of each of these simulations. Well, I was supposed. This was supposed to be animated, but let me change that. Okay. So in tension, if you do, you can see that that there are obvious differences depending on which interaction you use. The Taylor or the very stiff interaction, which is the secant and the full constraint, the Taylor, tell you that the tensile axis tends to align the grains with the 1-1-1 orientation, or the 1-1-1 orientation of the grains tend to align with the tensile axis, in which case you are activating 6 systems per grain, and or with the 0-0-1 axis, in which case you are activating 8 systems per grain in these ideal situations. All the other methods, affine, n effective equal 10, tangent, tend to spread the texture there for the reason that I explained before. Now, the other interesting thing is that in compression, you see that the tendency is for the 1-1-0 direction of the grain to align with the tensile axis. However, there is a shift here, which is not so obvious here in these simulations, in the tangent. You see there is a shift here that is not there. Well, that has to do with the effect that I was explaining before. That in a more compliant cases, or when the medium is more compliant, the grains don't want to deform in axisymmetric deformation. They want to deform more in plane strain, and so that is what leads to these differences. This difference in texture. Now, you can also access information about this because in the stress strain file, is in the stress strain file? No, there is a file where you can look at the deviations of each of the stress and strain component, the deviation with respect to the average. And it is very clear when you go there, look at the deviations between the average and the grains, that what is going on with those components. So, as I said, the exercise will be run the secant and the tangent case. I put the other one, I put just for you to do later if you want. Run the case n effective equals 0.1 and n effective equals 50, because that allows you to show that you can control the compliance of the medium. With n effective equals 0.1, what you are doing is you have m secant, and you're multiplying it by n effective. So m secant is already very stiff, but if you multiply it by 0.1, you make it even stiffer. So it's less and less compliant, more and more stiff. Now, if you multiply it by 50, you make the problem the compliance of the medium very compliant, and then you are going towards the Sachs. So this one goes towards the Taylor model, and this one takes you to the Sachs model, and that is the n effective. But that is something that you can try yourself later.